For many years, scientists recorded measurements in metric units, which are related decimally, that is, by powers of 10. In 1960, however, the General Conference of Weights and Measures, the International Authority on Units, proposed a revised metric system called the International System of Units, which we abbreviate SI, from the French Système International d'Unités. The terms mass and weight are often used interchangeably, although strictly speaking they are different quantities. Whereas mass is a measure of the amount of matter in an object, weight, technically speaking, is the force that gravity exerts on that object. So, for mass, which is the measure of a quantity of matter, the SI unit that we use for it is the kilogram. So that's the standard unit that we go off of. And 1 kilogram is equal to 1,000 grams, or 1 times 10 to the 3 grams, when you express that in scientific notation. Now weight, on the other hand, like I just said, weight is the force that gravity exerts on an object. And the way that we calculate weight is using this formula here, that weight is equal to the acceleration of gravity, this constant c, multiplied by mass. And so something's weight on Earth, if we have our gravitational constant at 1.0, on the moon it's about 1/10 of that. So that means that a 1 kilogram bar that weighs 1 kilogram on Earth, okay, since the gravitational force is much less on the moon, it's only going to weigh about 1/10 of that, right? Because we multiply by this factor. And so on the moon, a 1 kilogram bar from Earth is only going to weigh about 100 grams, or 0.1 kilograms. This table shows the 7 SI base units. All other units of measurement can be derived from the base units. Like metric units, SI units are modified in decimal fashion by a series of prefixes, as we're going to look at in a few minutes. Let's take a look at all of these base units. For length, we use the meter. The symbol we use is a lowercase m. For mass, the base unit is the kilogram. We use kg for that. For time, it's the second. We use a lowercase s. For electrical current, we use the ampere, which is a capital letter A. For temperature, the base unit is Kelvin, for which we use the capital K or uppercase K. For the amount of a substance, we use the mole, M-O-L-E, and we abbreviate that by just removing the letter E to M-O-L. And then for luminous intensity, we use the candela, or we abbreviate that as CD. In chemistry class, the ones you're going to see the most are going to be length, mass, time, temperature, and amount of substance. Like metric units, SI units are modified in decimal fraction by a series of prefixes that are shown here. We're going to use both metric and SI units in this class. Volume is an example of a measured quantity with derived units. The SI derived unit for volume is the cubic meter. And the way that we represent that is with m to the power of 3, like that. Generally, however, chemists work with much smaller volumes than cubic meters. So generally, we like to use the cubic centimeter or the cubic decimeter. So 1 cubic centimeter would be represented like this, 1 centimeter to the power of 3, and 1 cubic decimeter would be represented like this, 1 dm to the power of 3. Another common unit of volume is the liter. And for liter, if we had 1 liter, we would represent it like this, 1 L, like that. A liter is the volume occupied by 1 cubic decimeter. So we could say that 1 liter is equal to 1 decimeter cubed. 1 liter of volume is also equal to 1,000 milliliters or 1,000 centimeters cubed. And I have all that summarized right here. So 1 liter is equal to 1,000 milliliters, 1,000 centimeters cubed, and 1 decimeter cubed. Another thing that you've probably already figured out is that 1 milliliter must be equal to 1 cubic centimeter. The figure shown over here on the left compares the relative sizes of the two volumes. Even though the liter is not an SI unit, volumes are usually expressed in liters and milliliters. Over here on the right, I have a picture of a volumetric flask, and you can see, it might not be easy to see, but you can see here it says 25 milliliters. And so the important thing here is to know that oftentimes when chemists work in the lab, they usually will use milliliters for their volumes. Density is another measured quantity with derived units. The equation for density is shown here in this black box. Density is equal to mass over volume. We can shorten that to D is equal to M over V. Of course, the D represents density, M represents mass, and V represents volume. The SI derived unit for density is kilograms per meters cubed. We are not going to use that very often in a general chemistry class. What we usually use in our class is going to be either grams per centimeter cubed or grams per milliliter. And since 1 centimeter cubed is equal to 1 milliliter, you can see that 1 gram per centimeter cubed or 1 gram per milliliter cubed is actually equal to 1,000 kilograms per meter cubed. It's also important to point out that density is an intensive property and it doesn't depend on the quantity of a substance that we have. So that means that if I have 1 centimeter cubed or 1 milliliter of water, or if I have 10 liters of water, the density is going to be the same, again, because it's an intensive property. This table lists the densities of several substances. For example, you can see that water has a density of 1.00 grams per centimeter cubed. Now this is measured at 1 atmosphere, so that's basically at sea level. You can see that something like ethanol, which is found in alcoholic beverages, has a lower density than water. But if you look at something like air, it has a much lower density than water. In fact, it's 1,000 times lighter than water. If you look at these metals down here, things like iron, lead, mercury, gold, osmium, you see that they have much higher densities than water, ethanol, and air. In fact, osmium is the densest element known in that it weighs 22.6 grams per centimeter cubed. That means it's about 23 times heavier than water. Let's take a look at a question. It says gold is a precious metal that is chemically unreactive. It is used mainly in jewelry, dentistry, and electronic devices. A piece of gold ingot with a mass of 301 grams has a volume of 15.6 centimeters cubed. Calculate the density of gold. A gold ingot is basically just like a little gold bar. Anyhow, we're asked to calculate the density, so we're going to use the formula. Density is equal to mass over volume. We already know the mass. It's been given to us in grams. This is our mass. And we're also given the volume in centimeters cubed. So here's our V. And now we can just plug those numbers into the formula. So density is going to be equal to 301 grams divided by 15.6 centimeters cubed. And when I punch that into my calculator, I get 19.3 grams per centimeter cubed. That's the density of my gold ingot. And if you go back to the previous slide, if you look at the density of gold, what do you know? It's 19.3 grams per centimeter cubed, so our answer seems pretty reasonable to me. Let's take a look at another problem. This is the same kind of problem that you would run into on an exam. It says here the density of mercury, the only metal that is a liquid at room temperature, is 13.6 grams per milliliter. Calculate the mass of 5.50 milliliters of the liquid. Well, we're going to use our formula D is equal to M over V, but this time we're given the density, so we're given D, and we're given the volume. So we're also given the volume, and we want to calculate the mass. And so what we're going to have to do is we're going to have to rearrange the formula to solve for M. And so we're going to multiply both sides by V, and that means that V will cancel out over here, and what we'll end up with is that mass is going to be equal to density multiplied by volume. We can double check our algebra here when we take a look at the units. So let's plug in our density, which is 13.6 grams per milliliter, and we're going to multiply that by the volume, 5.50 milliliters. And look, our milliliters cancel out, and we're left with 74.8 grams. So we're left over with grams, 74.8 grams. So there you go. That's the mass of the mercury. 3 temperature scales are currently in use. Their units are degrees Fahrenheit, degrees Celsius, and Kelvin. No degrees. The Fahrenheit scale defines the normal freezing and boiling points of water to be exactly 32 degrees Fahrenheit and 212 degrees Fahrenheit. The Celsius scale divides the range between the freezing point of 0 degrees Celsius and the boiling point of 100 degrees Celsius. As we saw in a previous slide, Kelvin is the SI base unit of temperature. It is the absolute temperature scale. By absolute, we mean that the 0 on the Kelvin scale is denoted by 0 K, the lowest temperature that can be attained theoretically. Now, the Kelvin scale that we will use a lot in general chemistry, we see that the freezing point of water is 273 Kelvin, and if we add 100 to that, we get the boiling point of water in Kelvin, which is 373 Kelvin. So that means that the difference between 1 Kelvin and 1 degree Celsius is the exact same. So they go up by the same scale. The difference is that when we drop all the way down here to 0 Kelvin, this is what we call absolute zero. This is the point where there is no molecular motion at all. And so again, Kelvin, or the Kelvin scale, is the SI base unit of temperature. Now, the size of a degree on the Fahrenheit scale is only 100 over 180, or 5/9 of a degree on the Celsius scale. If we want to convert from degrees Celsius to degrees Fahrenheit, we would use this equation right here. Another thing that it might be good for you to do is try to rearrange this equation to solve for degrees Celsius. And when you do that, you would end up with degrees Celsius is equal to degrees Fahrenheit minus 32 multiplied by 5/9. Again, it would be a good idea to check to make sure you have the necessary algebraic skills to be able to do this. Also, if we want to convert from Kelvin to degrees Celsius, we use this formula right here. The Kelvin is equal to our temperature in degrees Celsius, and then we add 273.15. And again, the reason why is because 273.15 Kelvin is equal to 0 degrees Celsius. Oftentimes we'll use only 3 significant figures and just use 273 Kelvin is equal to 0 degrees Celsius. Let's try a question. Solder is an alloy made of tin and lead that is used in electronic circuits. A certain solder has a melting point of 224 degrees Celsius. What is its melting point in degrees Fahrenheit? Well, to solve this, I'm going to use the formula that was shown on the previous slide, which is degrees Fahrenheit is equal to degrees Celsius multiplied by 9/5 plus 32. You're going to have to know this formula for your first exam. And now I'm just going to plug in my numbers. I know my melting point in degrees Celsius. It's given to me right here. And so I'll put in 224 degrees Celsius multiplied by 9/5. Then I'm going to add 32 to that. And when I put all of that into my calculator, I get that the temperature or the melting point in degrees Fahrenheit is equal to 435 degrees Fahrenheit. So that's going to be my melting point of my solder in degrees Fahrenheit. Let's try another one. Helium has the lowest boiling point of all elements at 452 degrees Fahrenheit. Convert this temperature to degrees Celsius. So what I'm going to do is I'm going to use the formula that I derived a couple of slides ago, that degrees Celsius is equal to degrees Fahrenheit minus 32 multiplied by 5/9, like that. So now I'm going to plug in my temperature in degrees Fahrenheit, which is 452 minus 32 multiplied by 5/9. And when I punch all of that into my calculator, I get the boiling point of helium in degrees Celsius, which is 233 degrees Celsius. Again, this is another formula that you're going to have memorized, or you're going to have to derive it on your first exam and probably on your final exam as well. Let's try another one. Mercury, the only metal that exists as a liquid at room temperature, melts at 238.9 degrees Celsius. Convert its melting point to Kelvin. And for that, we're going to use our formula, which is Kelvin is equal to degrees Celsius plus 273.15. So we're going to put our melting point in degrees Celsius, 238.9. We're going to add 273.15 to that, and we get that our melting point in Kelvin is going to be equal to 512.1 Kelvin.